Hello and welcome to the Open Source Silicon stream, and today we're at number 18. So if you've not been to these streams before, then welcome. I'm Matt Fenn, host of the stream, and I am an electronic engineer and science communicator, and I got into ASICs about 4 years ago, thanks to the Google-sponsored free tapeouts. I did about 20 tapeouts and built a couple of courses. You can check them out on the Zero to ASIC course. And the idea of those is to take people from beginner zero to doing their first tapeout. And since then, I've started a service called Tiny Tapeout. I'm actually wearing a Tiny Tapeout. Tiny Tapeout. And the idea there is to make access to silicon as cheap and easy as possible. So that's enough about me. Hi, Sylvan. Sylvan says hi. Good to see you here. And Sam says hi as well. The idea of these streams is to share news, share some interesting stuff, and then usually there's a kind of main topic. And today the main topic is I'm going to attempt to submit something to the new RISC-V peripheral competition. So we've done a few competitions with Tiny Tapeout to encourage people to get started and get involved with a group of people doing some cool stuff together. Previously, we've done the demo scene competition where you plug the ASIC into a screen and a sound system, and then you watch the demos. So we're actually still waiting to get silicon back so we can do the final judging. And this competition is the RISC-V peripheral competition. So we provide a RISC-V core that's designed by someone in the community, Mike. And then we've got an 8-bit and a 32-bit interface, and you can build a peripheral and it gets plugged into that CPU. And then we'll essentially be building an open source, crowdsourced RISC-V microcontroller. I've got some quite interesting people that I'm hoping going to be judges for that. So watch the space. I'll be announcing them soon. And yeah, after the news today, I'm going to try to build a peripheral that I can then submit into the competition. So let's share my screen here. So for previous episodes, if you want to get a look at the kind of resources that I'm sharing and check the links, the Google Doc that is linked in the description of the video below will take you to this. And you can get a list of all the previous episodes there. And done the intro, now it's the news. So a couple of weeks ago, I went to the Free Silicon Conference, and it was at a great venue, which was the IHP semiconductor factory in Frankfurt der Oder. And as well as the great conference, we also had a series of lab tours. And I've been there before. If you might have seen a video that I produced that was visiting the clean room and seeing how they build chips over there. And it's super cool now because we're doing open source chips through them. So I was actually able to handle some of the wafers that have designs on from people in the community, and then also take a look at those designs like midway through manufacturing. I got to see them just at the level after they'd finished the MOSFETs, but they were just starting the first metallization. And I'd always been obsessed with the clean room, and I'd forgotten that at IHP they also have all these other labs, and a great part of the conference was having the invite to visit these to go on these lab tours. And I asked permission to take photos, and I just got permission to share them. So I wanted to share some of these here and talk a little bit about some of the stuff I saw. So let's just start here. So this was the offline characterization. I'm going to just try to solo this now. There we go. Hopefully you can still hear me. Otherwise, I'm sure you'll let me know in the comments soon enough. And this is a nice high-res picture. We can actually see up here. This is in the offline characterization lab. And this machine is secondary ion mass spectrometry, SIMS. And At the front here, you can load in a wafer. Here's one of the wafers that they were using in the test. These little bottles here contain the beryllium source, and that gets loaded in up here. And then it's basically used as a particle accelerator to blast down, hit the wafer, and that can be scanned a bit like a scanning electron microscope. And that will then knock off atoms on the silicon wafer, and they get sucked up here as part of a mass spectrometer. So very, very quickly, the machine can find out the chemical composition, the elemental composition of the wafer. And the beryllium atoms can also be used to kind of etch down through the wafer. So what this machine basically allows you to do is to build up a cross-section through the wafer of all the atomic weights that are present. So, for example, you can look at the diffusion of the N and P regions of a transistor and check that that matches what you're trying to make in the lab. Didn't know that that kind of machinery existed, to be honest. It was really cool to see that, and great to see on the monitor. I didn't take a photo of the screen, that you could see the density of the N and the P and the N. So that was super cool, very interesting technology. So if you've not heard of it before, check out SIMS. That's the search word, the keyword. Nice poster here. It'd be good if there was a little QR code we could scan to get full res of that. Maybe I'll ask for that next time. In two labs over, they had this machine, and this is essentially the same machine, but 25 years older. So one of the big differences that's happened is that things have just got smaller. Hi, Rohan. Welcome to the stream. Good to have you here. And this one also, but they still use this one, and this one also had advantages in that you could load a cartridge of wafers into here, so not just one at a time, and then the machine could kind of transport them from here into the main scanning imaging part and then back out again. And this part up here was the magnet, so you can kind of see just how big those things were 25 years ago. And magnet technology has improved a lot, and now it can all be fit into a machine a lot smaller. Apparently 2 or 3 million euros for a machine like this. If you want to save up, start saving your pocket money. And then the only other lab, I think they had 6 labs, but we had to choose only between 2. So the other lab that I chose to visit was the where you can test the wafers that come off the end of the line. So again, here's an example of a finished wafer, and they do a lot of multi-project wafers. And here, for example, at the bottom of the screen, you can see like a blown up picture of all these little designs that then go and make up the one big design that is then patterned across the entire wafer. So when you slice this wafer up, it's got all of these individual things on it. Hi, Jörn. Welcome to the stream. And Brad says, what's 50 Bitcoin between friends? Is Bitcoin now that much? I got a friend actually who back in the day ordered a pizza with Bitcoin, or they like split the bill with Bitcoin or something. He like set up his wallet and did it for just this one thing, and then never used it again. Then like 10 years later, the kind of quarter of a Bitcoin that he had left was worth 4,000 or 5,000 euros. So he cashed it in. Not enough to buy one of these, unfortunately. Damn, 115K. It's wild. So if you want to check if the designs are working, you can use one of these machines, and it's kind of split into 2 sections. The thing on the bottom handles the wafers, so you can load in a rack of 24 wafers, and it can move them all around and get them into the correct position. And it can also go hot and cold. So you can do industrial temperatures to check that things are working across the temperature ranges. And then the thing on the top is a very big, fancy oscilloscope that has hundreds of channels, and it can also provide test stimulus that's then controlled by a computer. And that, if you split this machine up between this top and bottom part here, this is the interface. So that top bit comes down and rests on these three big chunky pins here. And then if we zoom in, these are all the landing pads for hundreds of little pogo pins that come down from that top section and connect onto here. And then this is held in place on top of this bottom wafer handling machine with these big clamps here. And you undo those, lift this top part off with a handle here. And the final thing is this. This is showing the bottom side. And then in the middle here, this is actually what then touches down on top of that silicon wafer. So the wafer is moved and then pushed up so that each of these are tiny, tiny thin pins, and they come to rest on the pad frame. So let's just go to this decap picture, just so you can see. So if we just change to the GDS view here, so all of the designs are kind of like in the middle, for Tiny Tapeout at least. And then round the outside, you've got the pad frame with all the IOs. And then on top of these is going to be a little piece of metal. We go back to the microscope view. I wonder if those have all been kind of ripped off, because that's where the bond wires would have come down and bonded onto here. They might have been pulled off and pulled that metal landing off. But those needles here all come down and land all the way around and provide power and provide the test stimulus, and then can read out to see what's happening. So if you've got JTAG or something like that on your chip, you can power it up, you can run it through temperature ranges, you can put in your JTAG, you can read out the response and check that your design's working. So that was really cool to see. I'd not seen one of those machines close up before. So it's really fantastic to go to IHP, and I want to just say thanks to IHP for letting me take photos and share the photos with all of you. And also what's cool is they're gonna let me come back and then tour all 6 of the labs, because they also have things like the high frequency. They do like 500 gigahertz transistors in this lab. So if you're doing that, you also need the equipment to be able to measure, is it working or not? So they have some pretty amazing high frequency radio test gear there as well, and anechoic chambers and all that stuff. So I'm looking forward to going back and then being able to do a series of videos in each of these labs. Sam says, that's a crazy probing setup. We sometimes land 3 or 4 pins for stuff at our lab. Yeah, I did ask, because I was wondering about the loop inductance. Like if you've got these wires, then they go out to here, and then they go through this board, and then they get connected through the pogo pins, and they get connected up to here. And that's where all the scope electronics is. Then you've got some, a fair amount of parasitics and inductance there. So I was wondering, how do you do super high frequency stuff? And he said that for doing RF stuff, you usually just have like a few probes that come in. So maybe, I don't know what kind of stuff you're doing, Sam, but having like a wafer prober where you just have like a couple of probes that come down, I think is quite normal for high frequency stuff. Sam says, we usually de-embed our probes. I don't actually know what that means. So if you want to explain what that is in the comments, Sam, that'd be cool. Okay, so that's what I wanted to say on IHP stuff. Couple couple of other little bits of news. One is not there, not there. Just Tiny Tapeout. So just a reminder, we've got 2 shuttles open, IHP25B and Sky 25A. So if you want to submit a design, get your designs in. 42 days and 56 days left, respectively. And if you had a design in Tiny Tapeout 8, 9, or 10 that was affected by the eFabless shutdown, then you should have already been offered coupons or replacements. But if you want to resubmit your design, you'll actually have to do that yourself. But if you haven't got a coupon or you haven't heard about this and you were affected, then please reach out to us. We'll make sure that you can submit your design back on one of these future shuttles. So Sam's come back and said, test structure internally in the chip, short open 50 load, assist a reference plane for the test setup. Yes, okay, yeah. That makes sense, because you don't want to do that stuff kind of far away from the chip. You want all of this inside. It's kind of like, in the early days, I did an interview with Andrew Zernenberg about testing one of the Open RAM macros. And it was difficult to test because it was the Open RAM macro and then just wires out to the pad frame. And then it's difficult to drive the signals fast enough. In fact, you can't drive them fast enough through the pad frame. You would need to come in through some other probes. But probably even better, you want your actual test to be next to the RAM and do the actual testing and characterization kind of as a built-in self-test or something next to it to do the measurements. And if you're interested to find out more about that, then check the YouTube channel, search for Andrew, probably is a good, let me just see if I can find it. Andrew Zernenberg. 0 to ASIC. Yeah, characterizing Open RAM with Andrew Zernenberg. So he did like a set of 3 interviews that ended up with his test results. So if you want to find out more about that, I'll drop the link there. All right. So yeah, that's shuttle news. And then the last thing, and we use it as a segue into the main topic of the day, is the RISC-V competition. So this is here. Build a peripheral, get it on silicon. Join the open source RISC-V peripheral challenge. We workshopped a couple of taglines last time. I think this is one of the better ones that we came up with. Sorry, I didn't use your ChatGPT one, Sylvan, but if you've got any more suggestions, keep them coming in. So yeah, we're going to build a crowdsourced open source RISC-V microcontroller, and that's going on to the Skywater chip that we've got coming up that we're fabricating via Chip Foundry. So that Chip Foundry is a new company that started up by 2 of the guys from eFabless, Jeff and Mohammed. So if you're interested in buying an entire MPW slot, definitely check them out. 24 out of 40 slots reserved, so that's great. 34 planned out of 40, so that's great. That's $15,000 for 100 QFN chips. And if that's too much, then this is a way of getting involved for free. So entrance to this competition, you can submit a small 1-tile size design, and you don't have to pay to submit that. So you can check out the rules here. I'll drop the link in the comments there. And if you want to get all the details, then you can also check last week's stream when I had Mike Bell, the author of TinyQV, on the stream, and we had a chat through it. We looked through these 2 different options. And what I want to do today is submit a very simple peripheral to this competition. So eat our own dog food, see if I can follow our own instructions and put something simple in. Brad asks, have you heard of this project? I don't know what this project is. And trig functions, as in, I suppose, sign on a microcontroller. I mean, this isn't really a microcontroller chat. I'm sure there's plenty of people who know about microcontrollers here, though. But we're mostly focused on ASIC and I suppose FPGA stuff on this channel. In the name, 0 to ASIC. All right, so let's put this back on. Right, RISC-V competition. So I'm going to do a quadrature. So as part of the 0 to ASIC course, I have this RGB mixer that I always submit to our ASIC builds, Tiny Tapeout, and it's one of the practical labs of the 0 to ASIC course I mentioned earlier, part of the digital course. And essentially it just reads 3 Quadrature encoders, digital rotary encoder, and uses that to control a PWM driver, and then drives a red and a green and a blue LED together. So it's just like a basic getting started Verilog project. And I saw in the competitions channel, I was thinking of doing a WS2812 LED driver, because I've also done one of those before. But we had this great entry by Zero. I'm sorry if I'm getting that name wrong, and I feel bad about this because we actually met at the Free Silicon Conference and I got a lesson in how to pronounce his name. So if you're watching, I'm sorry if I've got your name wrong again, just ping me and let me know. But Zero also did a really cool SPI peripheral that actually Mike has leveraged as part of this competition. And Zero's now submitted a WS2812 peripheral to this project. So my idea is now just to take the rotary encoder part of this RGB color mixer project, wrap that up, makes it a RISC-V peripheral, and then with a little bit of firmware and using Zero's WS2812 driver, I'll be able to rebuild my RGB mixer project, but with a RISC-V in the middle and using the intelligent LEDs instead of just normal ones. So that's my plan. And I'm going to try and do it now in like 35 minutes. So wish me luck and help me out in the comments. I still feel kind of nervous about these things because in my experience with hacking hardware or hacking FPGAs, I can often like hit a brick wall that will just stop me for like an entire hour. And I really feel like that doesn't make for a fun stream to watch. So I try to prepare myself a little bit in advance. So I hopefully won't get too stuck here. So what I'm going to do first, I think, is just to show you what I've got. I've got this project running on the FPGA. And the first thing was just to show the debounced rotary input signals. Actually, what I might first do is just show the A and B signals of the encoder. So I think I can just twizzle the knob and you should be able to see this. So for people who don't know about these kind of digital encoders, basically as you twist the knob, That's a little bit confusing. Turn that off. You see that the green goes low, followed by the blue, and then the green goes high, followed by the blue. And that means that I'm turning one direction. If I turn the knob the other way, see the blue goes low and then the green. So with a little bit of logic, we can tell which way the knob is being turned, and then we can count and increase and decrease. But because these encoders are fairly noisy, we need to debounce them. So to show you what I mean by noise, let me just zoom in and twist the knob again. So some of these are high enough to trigger that input, and then we're going to get noise propagating through the logic. So what I'll show you now is connect up the debounced signal. So we're going to see the blue. I'll turn off the green, so you see the blue and then the debounced in yellow. That's a good one. So you see all this bouncing noise, but we just get one clean edge into the encoder. Rohan says RGB mixer, but with WS2812. Yes, and way more complicated. So instead of just piping one to the other, there'll be a RISC-V in the middle that is reading from one peripheral and then writing out to another peripheral. So there's one thing I really like about Mike's work on this project is that we can have multiple peripherals and have them all, they'll all be active at the same time if you want, all with different addresses. So I can just write a C program that is constantly reading the register of the encoder, like what number it is, and then writing to the WS2812 channel to set the color. Brad saying, can you talk to offline, talk on Discord? Yeah, there's the Tiny Tapeout Discord, but probably not the right place for microcontroller stuff. Try to keep it focused on ASIC and FPGA stuff. Okay, so then the last thing to show is just the PWM output. So I'll connect that now. So you see, as I twisted that knob, the yellow PWM waveform got higher or lower duty cycle. So we've seen it working on the FPGA. And if you're interested in the source, I drop a link here to the source. And one thing I just added today was a strobe signal for the debounce, because I want everything to run at 60 megahertz. That's the frequency that the RISC-V is going to run at. And my debouncer basically is just a shift register, normally 8 bits long, and it's reading into that and if every flop in the shift register is high, then we get a debounced output. So it's delayed. And that's why there was that little delay we saw in the scope signals. But if this is running at 60 megahertz, then it's basically not doing any debouncing. So I just added a strobe input, so a bit like a clock gate. So only every kind of, I only want this to run every like 5 kilohertz or something like that. So I can generate a strobe signal that happens every 10,000 or 100,000 clocks or whatever. And then the strobe, I'll get a one coming in for 1 clock cycle, and then this will operate 1 time. And then I don't have to have like an enormously long shift register. Sam's recommending Charles Law's Discord for C stuff and microcontroller stuff. I think that's a great suggestion. Okay, so I've got my strobe generator, and I've got my debouncer, and I've got my encoder. That's the last thing. So here's basically just saying, on every clock cycle, put the old value of, so with a quadrature encoder, you've got these 2 signals. We saw them on the scope, A and B, they're normally called. So have a previous and a current. So and because we've got those edges cleaned up, every now and then we're going to see A and old A being different to each other. And then I can have a simple state machine here that is basically saying, if we're transitioning, let me just increase the font size a bit here. If we're going, if B's not changed, but A is gone from 0 to 1 or 1 to 0, then we should increment. And the reverse here for B. So that's my encoder state machine. So I'm going to take that and the debouncer and the strobe generator, and then I'm going to try and put them in into Mike's competition. So to do that, I'm going to do the byte peripheral because I don't need interrupts or 32-bit data. So I've got to, and there's some good documentation here. So need to rename the peripheral, create a test script. I'll probably come back to do the test. I'll just try to get the hardware working today. Replacing the implementation in the example with your own implementation. So let's start off by creating a new repository. Encoder. So this is the wrapper here, and I think I don't change any of this. This is what I change. TQVP. Tiny QV RISC-V processor, I guess, TV encoder. So these are my input signals, and then I think that's the only thing I've got to do here. And then this is my peripheral. So then again, this needs to be says unique as well. So I might actually just change this to be Matt. Put my name in there. Matt encoder. Boom, boom, boom. Do you think I need to change the Verilog file name? Will that cause a problem when they're all merged together? Do I need to change this to like Matt's encoder for the Verilog? And then here's a read-write register. So I can use that register later to read the outs. And then here's when I'm going to instantiate my other bits and pieces. Okay, so debounce, encoder, and strobe gen. Unique file name. Yes. I'm just seeing that my face is kind of over the screen. That's not the right way though, is it? Maybe like that. Maybe I'll just have my, can I drag this somewhere? How about that? You don't get to see my lovely face anymore, but you get to see the whole screen. Probably more important. Mike says, thanks, Mike, for tuning in, by the way. Might probably make sense to change the file name for multi-file submissions. I'll ask people to put the files in a new directory. Okay. So I'll move this to mattencoder.v. And then this is going to have to include my stuff here as well. So that's changing. And then I need debounce.v, encoder.v, and what was the other one? Strobe gen.v. So I think those are the files. I should open that back up again. So down here, just realized I don't think I've set this up for like tabs versus spaces. That works though. So strobe generator for the debouncer. 2 debouncers, one for channel A and one for channel B. And then an encoder. And they're going to need some signals. Now I set this to 8. Now I want about a 5 kilohertz, 5 to 10 kilohertz here. So we're running at 60 megahertz. So the way I do this is natural log of 60 megahertz, natural log of 2 divided by that, and I get 25, 2 to the 25. Is that right? 60 no, hold on, 60 megahertz, and I want 5 kilohertz. Right, so I need like a count up to 12,000. So natural log of that, natural log divided by 2, so 13, 14 bits. So if I do 2 to the 14, I get 16,000. Yes, sorry, Sylvan, log 2. What I'll probably do in like as a something to do in the future to do make the width adjustable. Make the strobe frequency adjustable from the, so I could write to a register to change that. All right. I guess another thing to think about here is how many channels. For now, I'll just do 1, but there's no reason why I couldn't do 3, like an RG and a B. Let's just do 1 for now, though. Deep-band strobe encoder. Okay, so then this is going to be, I think I just can directly access the UI in just like I can on Tiny Tapeout. So maybe I'm going to do this with some like assigns to make it a bit easier. So wire enc 0a equals UI in 0. And B is going to be 1, just so that the mapping is done. Then I'm going to need those wires, which I've already got here. I don't need this PWM strobe because I'm not doing PWM anymore. Clock reset. So what's my reset? It's not reset. Okay, so I should do a wire reset equals not reset n, because this other stuff is positive reset. And then the output is enc 0. So that's the thing that needs to end up in this register. So for me, those were just wires. And then I think here I can just do 480, then that should be enc 0. And in the future, this would be enc 0, enc 1, enc 2. I'll come back to that. And this, so I don't actually need this then, I don't think. Comment that out for now. Might be useful for later for doing this strobe generation. And I'm going to just assign this to be 0. Okay, so what do you all think? I mean, it seems like it's that straightforward. Let's see what happens when I push it to Git. Are my actions turned on? Yes. Can it publish the pages? Now it can. Mike says looks all good to me. And one of the things I also really like about the way Mike's done this is I've got like a few options here. Let me just I'll blather on after I've submitted this stuff. Hold on. I'm going to need here as well. Rotary encoder peripheral. .64 megahertz. Okay, I was wrong about that. Top module. So I think I just leave that the same. Let's just check the instructions here again. Done that. I haven't done the test script yet. Documented the design. And multiple modules create a subdirectory. So actually, I guess I'm that's something else I've gone wrong, done wrong. Maybe I should do put these all in a subdirectory. Debounce and strobe gen to ink. Mike is saying no need to worry about subdirectory now. That's when you're making your PR, but I'll just do it now anyway. He says it won't do any harm. Pin out, nothing on the out, and then inputs is going to be ink 0 channel A, ink 0 channel B. The rest TB done. All right, so I think that is it then. And I need to reference TQVP mat encoder from ttwrapper.v. Yeah, I think I did here. All right. So picking up my chain of thought while these actions run is that these actions are like the tiny tape out actions. So I'll be able to, if I wanted to, submit this onto the Tiny Tapeout Sky 25A, and because of it's using this SPI peripheral that Mike has included here, and that's from Um, uh, Ciao. I know that's not the right way to pronounce it. Sorry, Chico. Please tell me after the stream. Um, this is the person I was mentioning that I met at Free Silicon Conference. So that's the SPI thing. So from the RP 2040, I will be able to write some Python or C that will talk through SPI and then be able to read the registers of the encoder. But for the competition, I submit a pull request onto um, the main repo. Let's just see if I can find that easily. Here. So I become part of. Now, are there any pull requests yet? Not yet. Maybe I can be the first. Then my design will be incorporated in, and it is like going to be one big project with all the peripherals, and then I can write the firmware and using Mike's RISC-V, then read the registers to find out what's in the what happened in the encoder. So I really like the way I can do kind of both ways. All right, that worked then. So wasn't really expecting that. 70% utilization. That's interesting. Wasn't expecting so much utilization. Oh no, this is that's the main one. That's not that's Mike's CPU core. That's not me. That's the one. Oh, but it also works. No, still wrong. Here we go. Right. Yeah, okay. Still working. GDS. Where's the GDS up to? Okay. Looks like it is just about done. Docs failed though, and that will be because I need to also, like a normal TT thing, need to do my docs. Oh, look at this. Good stuff, Mike. Quadrature encoder. Incremental. Okay, incremental encoder. That's what people are. That's the calling it. Okay. GDS failed. Pre-check failed. That's interesting. No OAuth token found for github.com. I think that is don't think that's related to my design, unfortunately. Maybe I can just try to reload this. Did the WS2812 was that running? Yes. Anyone watching have any idea why this my pre-check has failed here? No OAuth token for github.com. I have been having some success with this explain error thing. Ah, rate limits. Maybe I've missed that. Yeah. Just the next line down, rate limit. I've been noticing that more and more recently. So that will probably just work on the next push because the GDS worked. The gate level test, what happened there? That probably failed the same way, did it? Oh no, actually it failed. Okay, I'm going to need to actually write it. Ken also has been getting rate limited a lot. All right. So let me push the docs here anyway. And then next step for me is going to be, let me open an issue here. Add additional 2 encoders. Add an adjustable throw rate for debounce. And add tests. I think I'm going to need the tests to get that other issue to pass. So I think, but that's, I think that's about it. Once, this is probably already in a position where I could now open a pull request. Okay. Raise a pull request. So I'm going to need to fork this. And then in source peripherals, I have to add my here we go. Here's the list of peripherals: GPIO, UART. So I'm going to add. I would basically replace one of these with mine. So I think what I'll do then is let me replace myself here. What I'll do is during this week, I will attempt to close those 3 issues. And then on next week's stream, which will probably be the last for the summer, because I'm going to take off a couple of weeks in the beginning of August, I'll make a pull request on Mike's repo so you can see that how the final step works. So thanks everybody for tuning in. Remember to like and subscribe and all that good stuff. Check out some of the other videos on the channel. Check out the courses I have. Join the Tiny Tapeout Discords. Get your RISC-V designs in, and look forward to seeing you all next week. Thanks again for joining. Bye-bye.